Hi, I'm Ben-Yaakov. This presentation is entitled Measuring the Loop Gain of a Switch Mode Converter by an Omicron Bode 100. Let me start off with just general background of negative feedback and as it relates to switch mode converters. Here I'm showing a very basic negative feedback system. This is the A open loop, this is the beta, the feedback, this is the summing junction, the input signal and the output signal. Now we know that the ratio between the output and input signal, the closed loop gain, is A open loop over 1 plus beta A open loop. Now the nice thing about it is that when beta A is larger than 1, that is, we have a loop gain which is larger than 1, then the gain converges to 1 over beta, because 1 can be neglected, and then we can take out A open loop, and we end up with 1 over beta. So this is the beauty of feedback. This is why we are using it. And if beta is stable, then of course we are going to have a stable input to output transfer ratio. Now the situation in switch mode converter is a little bit confusing. Let me go over it for a second. Here we have a typical closed loop switch mode converter. We have a power stage. It could be, say, a buck or a boost. And then we have a voltage divider. This is an error amplifier combined with a compensator. That is, there is some phase compensation involved here. And then we have an error signal coming into the modulator. This could be a PWM modulator or maybe a frequency modulator. That could be any kind. So this is basically the system that we have in switch mode converters. Now we can look at it this way. Here we have this divider. This is the case, the divider here. This is the, you might say, the power stage. And here I've combined the modulator plus the compensator. Okay, that's what we have here. Now I can redraw this thing this way. Here is now the compensator, this is the power stage, and this is the divider. Okay, so we see that in this system, in fact, the compensator is not beta. The compensator is in series with the power stage. Beta is in fact the K, the voltage divider, and of course if K, the voltage divider, is stable, which it is, then we get a stable output to input transfer ratio. So this is how the converter relates to a feedback system. Now in the case of a switch mode converter, we have a nonlinear system involved. That is the power stage and the modulator. Nonlinear power stage is transistor turning on and off. Modulator is producing, say, if it's a PWM, producing a pulse rate modulation signal. So it's rather difficult to handle, but what we can do is always look from the outside. For example, here, this is an analog signal. This is a linear signal here. It's a linear signal here. And here we have a linear signal at the output. So we can sort of put everything in a box and just look at the transfer function between here, which is a linear signal, and here is the linear signal, and then we can use ideas of perturbation and small signal analysis. Now, in the case of a analog control, this will be an analog circuit, but in case of a digital control, this already will be also a digital sort of a difference equation algorithm or code. And of course the modulator will be digital. And then we have this part here, which is linear, so we can handle the system from here to here and look at the transfer ratio of the whole system. Let me just add one more thing. The system is non-linear, so therefore what we can do when we analyze it, we sort of linearize it around a certain operating point. In this case, in order to get, say, the transfer function, we set V at a given value, and then we inject a perturbation, a small signal, V sub E, and then reproduce the output, which is DC plus the perturbation. Now inside, what we're going to see, if this is V sub E here, the signal, this is the perturbation, then what will happen, of course, is the modulator will start changing the duty cycle if it is a PWM, and therefore we're going to have a, as we call it, a small d, that is the deviation of the duty cycle around the operating point, and this has a magnitude and a phase and a frequency, so we can talk about small signal of the duty cycle. So this is how the switch mode converter relates to a feedback system. Now about stability, assuming a linear system at a given point, then we can resort to Nyquist or Bode, and I'm not going into the details here. There are some videos in my YouTube channel that discuss stability and compensation, so I'm referring the viewers to these videos. Here, just say that one criteria is, of course, assuming a minimum phase system that is with no zero at the right half plane. Then we look at the cross of the Nyquist of the unit circle. This is the unit circle, and here it is, which translates in Bode to this curve. This is the unit circle, okay, this is 0 dB, and this is the cross, and we look at the phase. This is the total phase, and as we know, the phase margin, that is the distance from 180 degrees, is a measure of stability, and in particular, if the phase margin is too small, then we're going to have, for a step excitation, we have to have an overshoot, and then in the frequency domain, we have a sort of a high Q behavior with a peaking here, and then this overshoot and this peaking is a function of the phase margin. The smaller the phase margin, the higher is the disturbance. So we would like to have the system working at say above 40-45 degrees with a phase margin of say 45 degrees and up. So it is clear that the loop gain plays a major role in the stability and the dynamics of a feedback system, and the question is, how can we get the loop gain? Now the loop gain will be the overall gain, that is from here, starting here, going all the way and back. So if this is the summing junction, then obviously the loop gain is S sub F prime over S sub epsilon, because this is the input and this is the output, and so this is the loop gain. So if we can have access to the summing junction and measure these two signals, then we can get the loop gain as the ratio between them. Unfortunately, in a real switch mode converter, it is very difficult to identify these individual signals, because the summing here is sort of in you might say in parallel rather than in series, and therefore it's very difficult to distinguish between what is the SE, what is the SF, and so therefore it's very difficult to get the loop gain from around here, which is sort of the area of the summing junction. So the way to go around it is to generate or create another junction that we control, and we know all the details of it. And once we have this junction, this summing junction, then of course again the loop gain will be all the gain here all the way here, that is this S sub F over S sub epsilon here. This will be the loop gain. Okay, so this is simple, the idea. The question is, how do we do it? And also the implementation is not that difficult. What we can do is, within the feedback path, to inject or to put in a voltage and excitation source. This is an AC source with an internal impedance of 0 or very close to 0. And this source actually acts as a summing point because the voltage here is the sum of this, plus the voltage itself, that is this minus this, might say, is equal to this. So this is basically a summing point. So the loop gain will be the voltage here divided by the voltage here, because the voltage here is sort of the input to the chain here, and then it comes out as V out, and then therefore this signal here or this signal here is what we are looking for, obviously, in amplitude and phase. And in the actual implementation, what we do put a small resistor such that we are not disturbing too much this ratio of R1 and R2, which is setting up, of course, the output voltage. This will be a much smaller resistor than these. And then via a transformer, which is called an injector, we are feeding in an AC signal. Well, we need a transformer because we need to inject here a signal, floating signal, not referred to ground, and therefore we do need something which is floating. This could be based on a magnetic transformer or some other means of a AC source which is floating. That is, it's not committed to any ground, that we can connect it here and here. This could be high voltage, of course. Okay, so if we have this resistor, then by looking at the voltage here and here, then we can get the the loop gain. However, one has to watch it a little bit, in that this point has to be at low impedance. That is, we have to be at an output here which is low impedance. The reason is that we want this signal here to be a result of this gain here. Now, if we have a impedance here, say a resistor R sub 1, then this VAC is also causing a voltage here. And this voltage then is added to what is coming from here. Now, if the gain is very high at low frequency, that's okay, but near the crossover point, this could cause an error. So beware, always put this resistor something like this, and so that you have here a low impedance. Well, this if this is a power stage, then obviously you have, say if it's a buck, you have a inductor and a capacitor. So you see here basically at high frequency the capacitor. So this is the impedance we are talking about, okay? So the measurement will be correct when this capacitor shows a high impedance, that is high frequency, and this is when we have the crossover. So everything is okay if you are sort of connected here to the output capacitor of the converter. So the way then we can actually do the measurement is to use an instrument, a test equipment, which is called network analyzer or frequency response analyzer, FRA. And this analyzer has actually at the minimum 3 terminals. One is the excitation that goes into the injector, here it is, and then 2 other terminals which are inputs, A and B, and you connect one to one side, one to the other side, and this instrument is capable of giving you the ratio of A over B, amplitude and phase. And this is exactly what we need, because this ratio is basically the loop gain. So this is the way it is done. Now, I'm now giving an example with a specific instrument. This is the Omicron Bode 100. It has a bandwidth of about 50 megahertz. Here is the basic instrument. This is the excitation output. These are the 2 A and B sense input. And this is a PC-based instrument, so that here we see on the screen the results, say, of a analysis that was done with this instrument. So it is connected by USB. Also, we need an injector. So this is the injector by Omicron, the BWIT 100. It's an injector that provides isolation, and it should provide, of course, a bandwidth which is compatible with the analyzer or close to it, so that you can run your analyzer. The issue that I wanted to test is how well is the analyzer capable of extracting the signal from noise or from interfering signal. Now, obviously, the voltage here, if you look at it, is very noisy. I mean, aside from the injection that goes all the way, and you see it here, there is a ripple here. It could be fairly high. So the analyzer is supposed to be able to extract with, you might say, a very fine filter, the frequency of excitation, and then to look at the amplitude and phase of this value here and here. So this will be a measure of how good is this network analyzer. Of course, they have in the datasheet numbers like signal to noise ratio, but what I wanted to see is something a little bit different, and that is how does it cope with distortion. So what we did is the following. We have set up a test circuit that looks like this. These are two diodes, and then we have the injector, so we have an excitation, and now we put A and B over these diodes. So we look at the ratio between A and B. Now, to do this and to get the value, the analyzer has to be able to sort of extract from these waveforms. These are the waveforms that we see here at different frequencies. That's a lower frequency, and that's a high frequency because of the capacitance looks like that. And so the analyzer has to be able to look at the sinusoidal harmonic, the first harmonic of the excitation, or the excitation itself, very accurately in amplitude and phase, extract it from here, and be able to give us the value, because when we look at A over B, this is for the particular frequency injected at this particular moment. But before doing that, we'll do a calibration. Here's the calibration, so that we know that we have a good zero with the cabling and with the setup. And indeed, we have, after calibration, we have a very good measurement. And now we do the measurement itself. And as you can see, it's very good. Excellent, as a matter of fact, up to 50 megahertz, everything is fine, no problem at all. Now, there is one more point that one has to bear in mind, and that is the following. When we do the measurement, we have an injection here, and then we have two signals which are measured, A and B. They are measured, refer to ground. That is, we are not measuring the difference between them. We're measuring this, refer to ground, this, refer to ground, and then we take the ratio between them, okay? Now, obviously, if you have a switch mode system here, has its own ground, this analyzer has its own ground, you are bound to have some common mode of ground noise, some potential difference between these two grounds. So this would be a common mode error that could contribute or could corrupt the measurement. Let's now go to a real measurement. Here I have a switch mode converter built around this LM2596 IC, which has a transistor, a switching transistor within it. It has everything in. You do have to put an inductor outside and a diode. Here is the feedback. This is this resistance ratio. This is the variable adjustable controller. What we did here is we replaced it with fixed resistors. Here you see the fixed resistors. One is 10 ohm and one is 1 kilo ohm. so that we have a certain voltage at the output depending on the reference inside. Here is the injector. This is the excitation here. Here's the injector, the excitation. Here's the two terminals we are going to put here and here in order to get the loop gain. So this is the calibration done. First of all, this is a run after the calibration. And this is now a run after calibration when we connect. There's supposed to be 0 here, but the ground now is connected to the ground of the power supply. We are sort of left with this error, but this is very, very important to check. After calibration, again, to put 0 at the inputs, connect the ground to the ground of the test system, and look now at the common mode signal. Here it's pretty good up to, well, I don't know, 8 megahertz, so we are in good shape. And here's the real measurement. So what we see here is the gain and the phase. This is sort of looks, and it is a loop gain of a DCM, discontinuous mode of operation of a converter. It's a buck converter. And here is the phase. This is the crossover here. And this is the phase. You see the phase is 110. So we have quite a bit of phase margin here. We'll see it in a minute. And here, there's some wiggling here. And it has to do with the resolution and the amplitude of the signal. And you can try to fix it by changing the amplitude of the signal as you run the analysis. So this is a variable source level that you change it as the analysis goes on, and this indeed improved very much the signal. So we have a very, very nice signal here. It's smooth and it goes, well, it looks like, as I've said, a DCM. And then we have the phase here. And what you can ask the analyzer to do is to give you a Nyquist plot. Now this Nyquist plot is it's very raw. The resolution here is not that good, just to show the very basic features. What we see here, this is what the analyzer gives us. Now they are looking at minus beta A or minus loop gain. We normally, or at least I am used to look at the positive, look at loop gain as a positive number at 0 frequency, okay? At 0 frequency, it's a positive number, and usually it'll have a 0 phase shift, and then as the frequency goes up, the gain decreases, and you got the phase shift, and then eventually you go to where we don't see here, the resolution is not sufficient to see this unit circle, and then we look whether we do encircle the -1. Here it goes the other way around, so we're talking about encircling the +1 clockwise and not anti-clockwise. And here is a zoom on around the 0, and here we see the trace coming up. This is now smaller of values. This is the unit circle. Here is the penetration, and indeed you get the phase margin here is 106, which is very nice. And then we have also the so-called gain margin or stability margin, which is the shortest distance to in this case, +1, otherwise we would have looked at the distance to -1, and it is like 0.8, which is okay. So this is what you get with the analyzer, and then in this case, you can rest assured that we are in good shape. Also, I didn't mention that it shows that the bandwidth of this converter is about 8 kilohertz. In fact, it shows here which is very nice. So we have an 8 kilohertz bandwidth, and the phase margin is nice. So in fact, the dynamics of this system is pretty good the way it is. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it'll be useful to you in the future. Thank you very much.